Hi guys. I did a little playing around with data from 2110 section, and so one hopes that you've got your data plotted. I know if we're using, excuse me, Google Sheets, we know it doesn't do a very good job of adding error bars. And I've gone ahead and let's see, here it is, chi-square. So I have gone ahead and into the next step. Now what the chi-squared is, it's just the residual squared divided by the error squared on the data point. And so if you think about it, remember that when you do a fit, you sort of try to not only have the equal numbers of, or at least add the distances above and add the distances below, which is the residuals, if you think about that for a moment. But on top of that, you try to go pass through all the error bars. And obviously the ones with the smaller error bars are not obviously, you may remember that you try the smaller error bars well are more important. Okay, first of all, they're more important. That's the conclusion. The point is that the smaller error bars are more controlled than the big error bars. And when we do it by eye, we try, but just as the some of the residuals had a weakness for when using computers, the sum of the residuals squared has the weakness that it gives all the data points equal weight. So if you think about it for a minute, when you're dividing by the error bar squared, and you can see that these like these points, let's see, they get ones with the biggest error bars. Well, wait a minute, that's a residual squared. So where is, well, I made an artificially large one right there. But what happens is the ones with the larger error bars have the smallest chi-squared, and that because you see, since it's being divided by the error squared, that so let's see, this is data point, let's see, x is 4 centimeters. Yeah, see, that's a pretty small one. So the bigger ones have a greater influence on the sum. That's what it's all about. And the big error bars have very little effect on the sum, like this one here, or let's the very end, 0.0081. When you add that to 1.4 or 0.15, it doesn't have a lot of effect. Now, another thing here is I used, and I've got something like this for Google Sheets. I don't know if it's going to work, but we have this thing called a solver. And oops, I forgot something. So what I did in this case is I tried to say, look, don't worry about forcing it into 0 here, because strictly speaking, we didn't measure 0. So then, because I wanted to see about this green line, and which I'll get to in a minute. And so I was able to get this 55, and you don't know it yet, but 65 is what is the number we were hoping to get. And well, I mean, we all have the same data, so you guys are get as good as I could have gotten. But let's take a look at what's going on here. First of all, let's restore a reasonable error bar here. Let's make it similar to the other ones. You see it's pretty small now. And now there's a way of having Excel do the fitting for you. So just like us, it's going to minimize the sum of the chi-square by varying the slope and the excuse me, y-intercept. I discovered I had to place restrictions on the y-intercept. The computer, it kept like it just went into la la land, as they say. We in the world of fitting, we say it stepped into a bucket. Because in this case, it's a two-dimensional fitting space. So you think of it as a plane, and then there may be more than one of those kind of parabola spaces now. Instead of being just something flat on the page, now with the two-parameter fit, you can think of those what do you call it? Damn thing, y equals x squared. Parabolas. Now it's like a well in the surface, like instead of just some single graph. And so let's see what happens if I solve it now. Yeah, so now it goes back to something more reasonable that I had before. See the slope, and in fact, when I had a very small error bar on this, because I mean, you could force it to be 0, huh? So we'll make the error bar like something like 0.5. And then, but you see how the influence, when I made the error bar on 0, that it forced this line to pass closer to 0. So we can do it one more time. And what it's doing, I said it minimizes. All right, so that's 41. I don't think it's fair to have no error on there. In fact, I think the ideal thing, now that I think about it, would have been to ignore 0, huh? That's a good question. It's always an argument when you fit. Do you ignore 0 or not? I mean, it's supposed to be 0. 0t should be 0 velocity, but we're not actually measuring it, right? So that's another story. So anyways, yeah, because I was just staring at it and I said, boy, you know, if I don't force it to go through 0, I'm pretty happy. In fact, what we could do is we can change this. And instead we'll exclude the 0 from the fit. I'm just so interested in seeing how to make this work. So we won't sum up. Oh, I forgot to say equal. Oh boy, I'm a dummy. And let's see, equals sum. Oops, open parentheses. Where'd it go? Chi-square, here we go. Okay, close parentheses. And let's run the solver. This ought to be interesting. Let's see what happens. And oops, something went wrong. So I thought that I eliminated the, oh, I didn't. Okay, I'm an idiot. Let's see, P7, we want to do P8. Okay, see, garbage in, garbage out. And so right, it minimizes the chi-square by manipulating the slope and the y-intercept. There it is, 56. Yeah, you see, I like that. There could have been, I got to think about it. Maybe there's something in our technique with getting the average velocity. Well, you know why I like this? Because it gets closer to the real number. It makes me happy. So here I took the average of our heights, the average of our lengths. I got an angle. I multiplied g times sine theta, 980 for g instead of 9.8. And so you would have thought then that once we found the slope, we plugged it back into the equation, that we should return 980. But what we actually return is 607. And so, which is a drag, and you say, wow, we were off by so much. What's going on? Well, what's going on is that the original lab was using a sled on a frictionless surface, and that would have slid along, and it would have followed this blue line. This blue line has the correct slope, and that is here, V sliding right here. This is the blue line here. So that's just time and multiplied by this, yeah, here, the slope, this is the slope here. And then, of course, I would, whatever slope this happens to be, I would be able to use the equation, oh yeah, g sine theta, and solve for g, and I would return 980. Now, I haven't figured out, I used the energy equation here because it was pretty straightforward. You're going to hate your lecture professor after you go through all the kinematics shit and then go through Newton's laws and applications, and then we're going to introduce energy, and it's really easier. Notice how the mass of the marble drops out, the radius of the marble drops out, and we just have this equation for the what's called the moment of inertia. That's sort of the equivalent of mass when it comes to rotations. And we end up with this 10�7 g times h. So then I use this as my g, and that's how I got these v's here. And I had to come up with this formula here to produce the t's, because when I used our t's, which are all full of error, I just got a bunch of dots that kind of matched up, and I wanted a straight line. So we're not really going to have time for that. But if you can figure out a way to graph that, that would be cool. And so at the end of the day, though, and I was really, I didn't go very out of my way to produce this. Let's see if that, I made two green lines. So one green line is this equation here, and then I just made another fit line. And I just eyeballed it, so it's close. And so 65 was what we were hoping for. We ended up with 65. Give me a minute. That would have been here. Oh well, I guess I haven't translated it into the numbers to compare here. This is the prediction. Yeah, that's the prediction, 65. We ended up with 56, which isn't too bad. And so with 56, we end up with 607. And I have yet to come up with I just have too many other things going on. But the point is to look at how these two numbers are pretty darn close to each other. So we actually took some pretty darn good data. We couldn't guarantee. I was thinking that maybe the marble was sliding some, but then it would have produced a higher slope. And again, I don't know why the y-intercept is offset like it is, but I think this is really, really interesting myself, being the uber nerd. And so there it is. And it's too bad we haven't had time to figure out. Well, I mean, again, if somebody wants to try and graph this, what else? How else would you do it? You have these. Yeah, you have to have a way of. I think if you just plugged in time here, 0 to 1, in so many steps. What would happen if we did that? Let's just do it while we're here. So we have to go, let's just say 0.2, 0.4. Oh, well, yeah. Okay, something's not right. I don't know what. But let's fill it in for a moment and we'll see. All right. That's a mess. So, the problem is that the equation here is a function of how high. So I took the x value and then converted it into a height, which was basically just dividing, opposite over adjacent. Yeah, so you multiplied whatever value x was times g sine theta, and that gets, sine theta, and that gets you the height. And then, but the thing is, we're graphing it according to time. So I had to figure out the exact time. And let's see, yeah, I mean, I could have used the real acceleration of gravity. It was quick and dirty just to be able to compare the 65 with the 56. Now that's something Oh yeah, well, what have we demonstrated? Well, we didn't get the right value, but if G wasn't constant, we wouldn't. I mean, this is not a great straight line fit, but if you have a sum of your chi-square, the ideal is 1. And so 3.43, that's pretty badass, actually. So we can feel reasonably confident that whatever is the parent distribution, meaning those dots are all scattered around, but they truly represent a straight line because the sum of the chi-square is so low. All right, there it is. I'm going to get this ready and I'll publish it.